All right, so let's do one more example on rational equations, and this one's going to be a little bit harder. So in the next example, we will have to actually factor the polynomial in the denominator first in order to see the factors to make our LCD. Now, we don't cover factoring in this course. It's assumed that you already know how to factor. So if you don't, or you need the review, you can see section P5 in your text for a review of factoring if you need it. And additionally, I also have a YouTube channel, and there is a co-rec course that some students take, some don't, that is labeled as MAT162-Section. And I do cover factoring in there. So if you want, you can also go to my YouTube channel and look at the factoring videos from section P5 in the 097 course. And of course, you could also just YouTube if you prefer to, and do it that way. So here I'm just going to do a basic factorization and just kind of go through the steps once. But again, we're not going to spend time factoring in this class. So if you need that extra review, I encourage you to check out your textbook or YouTube for some more resources. So let's consider the equations y1 equals 3 over x plus 6 plus 1 over x minus 2. And a second equation, y2 equals 4 over x squared plus 4x minus 12. Now, the subscripts for the 1 and the 2 don't mean anything. They're not squares or anything like that. They're just trying to tell us equation 1, equation 2. We're going to find all values for x for which these two equations are equal. So for them to be equal, what I'm going to do is actually start by setting those two equations equal to each other. So y1 is 3 over x plus 6 plus 1 over x minus 2. And then y2 is 4 over x squared plus 4x minus 12. Now, to do my LCD, I do need to have factors. So I can see one group here, x plus 6. I see another group here that's different, x minus 2. Now notice that because these denominators are more complex, I have to bring in the whole group. I can't just bring in the minus 2 there. Now this last piece though, I see squares, which means that I can factor this. So I need to do that next. So I know what my factors are. So when you factor, and I'm just going to do this here, you're going to look at your possibilities. So for x squared, the only thing that can work is x times x. And then for minus 12, so negative 12, I could multiply negative 1 times 12, 1 times negative 12, negative 2 times 6, or 2 times negative 6, or negative 3 times 4, or 3 times negative 4. And what I want to do is I want to find a combination of these such that when I FOIL this out, I get that plus 4x in the middle. Okay. And the combination that works in this case is going to be x plus 6, x minus 2. Or you could write it the other way, x minus 2, x plus 6. If you FOIL this out, you're going to see it matches. So x squared minus 2x plus 6x minus 12, and you get that matching positive 4x in the middle. So for factoring, we're just reverse multiplying. We're trying to break it back down into its factors, into those multipliers instead. So what happens here is that this product right here actually can get rewritten as x plus 6 times x minus 2. And notice that we already have those two factors accounted for. So this is why we want to factor first, because I don't want to add this whole big complex thing here into my LCD if I don't need to. So these factors are actually already there. I don't need to add it in again. So I'm going to do some work over here. What I'm going to go ahead and do is I'm going to multiply each of these pieces by my LCD. And I'm going to run out of room here. So here's the left side. I'm going to write the right side just underneath. I apologize. And then I'm going to start canceling. So notice here in this first group, the x plus 6 and the x plus 6 cancel. So I have this left. I'm going to go ahead and distribute that 3. So it's going to be 3x minus 6. And the next group, the x minus 2 is going to cancel. So I have the x plus 6 and the 1 left. So when I distribute through with that 1, it's not going to change anything. I get plus x plus 6. And on the other side, actually, both of these factors are separately going to cancel. And I'm left with just the 4. I'm going to keep simplifying here. So on the left, 3x and x is 4x. Minus 6 and 6 is actually just 0, so it cancels out. And I'm going to go ahead and solve. And I actually get the nice answer, surprisingly, of x equals 1. Now, don't forget here, you need to watch your denominators, right? I'm going to run out of room on this paper. So my first denominator was x plus 6. I need to make sure that is not equal to 0. And if I solve it, I just have to make sure that x is not equal to negative 6. I'm good there, right? My answer was 1. And then my second denominator is x minus 2 equals 0, or does not equal 0. So I have to make sure that x is not equal to 2. And again, I'm okay there. For my last denominator, you don't have to do this one because the 2 factors are already accounted for, right? We already did the x plus 6. We already did the x minus 2. So you have the 2 issues to watch out for the denominator. There won't be anything different because we have the same factors. So far, x equals 1 looks good. The last thing you may want to do is, again, plug it in just to check your work, make sure that nothing else weird happened along the way. I'm going to do that in blue. So I'm going to just try to do kind of the quick check here. And I'm going to replace 1 anytime I see an x. So it's going to be 3 over 1 plus 6 plus 1 over 1 minus 2. And on the other side, I have 4 over. It's going to be 1 squared plus 4 times 1 minus 12. So here I have 3 over 7, 1 over, let's see, negative 1, and then 4 over 1 plus 4 minus 12. So I have 3/7 plus negative 1, right? 1 divided by negative 1 is negative 1. And then over here, I have 4 over. So let's see, I have 1 plus 4 is 5 minus 12 is negative 7. Now, if you're good with fractions, you can probably do the rest in your head. If not, you can find a common denominator. So 3/7, 1 is the same thing as 7 over 7. So that would be plus negative 7. And again, that negative can go anywhere you want. So I'm just going to move it up top. And I do end up seeing that both sides are equal to negative 4 over 7, which is true. So this answer here really is a solution to our equation. So as you can see, these rationals can get a little bit long and cumbersome, but the best thing to do is to take your time. So if you take your time in the beginning, then hopefully you won't make any mistakes. Whereas if you rush, you may miss something or you may factor wrong, and then that's a big issue. So it's really important to upfront, just take your time, make sure you factor correctly. So double check that it matches before you move on. Watch your multiplying as you go through and your canceling and all that. And then of course, watch your denominators and check your answers. Now, one last topic here are types of equations. So I mentioned at the very beginning of the lecture that usually for most of our examples, we have one answer in these cases, but we have seen a no solution case. And there's also something called an identity case. So let's run through those definitions. Equations can be placed into, I guess I should say placed, categories depending on their solution sets. So an equation that is true for all real numbers, and we haven't seen this yet, is called an identity. Identities have infinitely many solutions. Typically, when solving them, what happens is the variable cancels out and you are left with a true statement. So graphically, we see that when we graph each side of the equation as 2 lines, they're going to be identical. And I'm going to do graphing in a second and go back and show you what this one looks like too. This is different than just when we graph equations in 2 variables and we get infinitely many points. So an identity actually means that every single number is a solution. Everything works. An equation that's not an identity but is true for at least one real number is called a conditional equation. And that pretty much happens for, I should say, almost all of our previous examples. So we did have one that was a no solution, but all the others are conditionals. And then an inconsistent equation is an equation that is not true for even, one real number. It has no solutions. So typically when solving them, what ends up happening with these kind of weird examples is your variables cancel out. And for inconsistent equations, you're often left with a false statement, or another way to get an inconsistent equation we already saw was if you had an extraneous solution or something like that. And then what happens is what's going to look like graphically is that the lines will never intersect or touch. So let me bring up Desmos for a second here. And I want to just go back to this example because I did note we should check this graphically using technology and or a table. And I want to show you what happens when we graph the left side of the equation and the right side of the equation. So I'm going to graph this as one equation in Desmos and this as the other equation in Desmos. All right, so bear with me for a second while I get everything up. All right, so you should see Desmos now. So I'm going to go back to our example 6. I want to type in the left side as one equation and the right side as the other equation, kind of like how the problem was set up. And I'll just use y equals on each side. So it's going to be 3 divided by, and it's, let's see, x plus 6 plus 1 divided by, and when I hit the divided by symbol, it just automatically goes to the denominator, x minus 2. And then on the right side, I'm just going to type in y equals again. It was 4 divided by x squared, let's see, plus 4x minus 12. Now, you can see the two examples, one is red and one is blue. And what I want you to notice is that they intersect right here. And they intersect at the x value of 1. And that was the answer we got. So, and one way that you can check your solutions to these more complicated examples is to graph the left side and the right side of the original equations as two separate equations in Desmos or another graphing tool, and see what happens with the x values, not the y values, because remember, we're supposed to just be in x here. So just the x values. And if you have an intersection like this, then you have a solution. So any place that these two sides intersect or touch, you're going to have an answer. So that's why you see that intersection at x equals 1. So this is an example of a conditional. Now let's go back to the other handout and I'll show you what happens when we have an inconsistent and when we have an identity. No, let's try that again. Okay. So here I have two equations, and I'm going to tell you that something weird is going to happen with them. And let's see if they're identities, conditional, or inconsistent equations. So you're still going to solve the same way. And oh, I'm too far up. Hang on. There we go. You're still going to solve the same way. So these ones are a little bit simpler, so you can probably see something weird is going to happen rather quickly here. But oftentimes you can't with many examples. So on the left side, I just distributed through, and then on the right side, I just rewrote it. Now I'm going to try solving, and I'm going to try to bring my 2x to the left here. And what happens is that it cancels on both sides, right? That's kind of weird. It cancels on both sides. So 2 equals 3 is what's left over. Now this is false. So when you have a false statement like this, it is automatically a no solution. And it is an inconsistent equation. Okay. So when this happens, usually, again, for new solutions, we like to write that null set symbol. So this is another way that you could get a no solution, not just with extraneous solutions sometimes. So that could happen if all of your answers are extraneous, then you have no solution like we saw in one of the previous examples. Or in a case like this, it just doesn't work. You try to solve it, everything cancels out and you have a false statement. So that's also a no solution. I don't want to flip around too much, but let me show you what the graph looks like there. And I'm going to graph the left side and the right side as two separate equations. All right, so for my first one, the left side was 2 and then parentheses x plus 1. And then on the right side, it was 2x plus 3. And notice that those lines are not intersecting. They're actually parallel to each other. They're never going to intersect or touch. And when they don't intersect or touch, you have no solution there. There's no common value for x that they share. So again, we're focusing on the x values here because we're technically in one variable. You can also use tables. So I would recommend you check out your book to see what tables can look like and how you can match with tables. I think the visual is really so much nicer. So that's why I'm focusing on that here. But your book also does look at what do conditional, inconsistent, and identities look like as tables as well. Okay, and let's look at the other one here. So here I have an example. And again, you're just going to start solving in the regular way. A lot of times we may not even realize that we have something weird going on. So I distribute that 6. I'm going to combine like terms on the right side of my equation. 6 minus 2 is 4, so 4x plus 6. And then I'm going to start solving. And just like before, when I try to get my x's together, what happens is they cancel on both sides. But this time I'm left with a true statement, which is different. And again, when you're solving, it doesn't matter the order you go in. If I did the 6's first and then the 4's, I'd have 0 equals 0. You still have a true statement. So when you have a true statement like this and your variable has canceled out, this is your identity. Okay. So all real numbers are solutions, which is pretty crazy if you think about it. So every single number works. It doesn't matter what you plug in. It's going to work in this equation. So again, it's a little bit unusual. The way your book formally writes it is the set x such that x is a real number. Okay, so this is how your book is going to express identities. So it's all x's such that x is a real number. So any real number. This is a form of set notation here. And this vertical line just means the words such that. So any real number works. Realistically, in the real world, you really should not be getting identities, right? So if you're trying to solve a problem in the real world, you shouldn't have that everything is a solution. That's kind of weird. So these tend to be more theoretical examples, but still something to watch out for as you're going through your text and as you're doing your homework. So let's look at the graph of this again one last time. And if you want to see the tables, you can check out your text. And I'm going to enter the left side and the right side as separate equations so we can see this visually. All right, so the left side here is 4x plus 6. And then, all right, so that's the first one. And then the right side is 6 parentheses, x plus 1, close parentheses, minus 2x. And notice what happened. The second equation is lying right on top of the first equation, right? They're the same equation. So that's why you have infinitely many solutions. It's really because it's the same equation on each side. They're the same. So everything's going to work. And again, in the real world, this is not something we typically see, right? You may see it theoretically in examples or in your text, but in reality, we're more likely to see inconsistent equation or system than we are to see an actual identity. All right, so there's one last example I want to look at. It's an application here. And this is just copied from your text. I thought it was easier with bringing in the graph and the equations. So if you read through the section opener in the text, you'll see that we introduce line graphs, indicating that, in this specific example is this one right here, and it indicates that persons with a low sense of humor have higher levels of depression in response to negative life events than those with a high sense of humor. So what this study was looking at was a person's level of humor. So do you have a low sense of humor or a high sense of humor? And then their reaction to negative life events and if they ended up with depression. So those with higher senses of humor had lower levels of depression than those with lower senses of humor. So they had higher levels of depression. And then along the x-axis, you're looking at the intensity of the negative life event. So a low negative event versus a high negative event, right? And I'm not part of the study, obviously, so I don't really know the background information too well here. But for instance, maybe a low negative event could be something like spilling coffee on yourself in the morning, or maybe a high event would be something really tragic, like a death in your family, or something like that, right? So looking at different negative life events and then the chance average or your average level of depression related to that. So you have your graphs here, and you also have your models as equations. So this is the low humor group, and this is the high humor group. In each formula, X represents the intensity of a negative life event, from 1 being low to 10 being high. And then D, which is along this axis here, is the average level of depression in response to that event. So here's our question. If a high humor group averages a level of depression of 3.5 or 7/2 in response to a negative life event, what is the intensity of that event? And then how is the solution shown on the graph? So notice here that we are first looking at the high humor group. So we're focusing on this group right here. Now our question tells us that the depression level is 3.5 or 7/2. So what we know in this case is D. So if I plug that in, we can see that we're solving for X here to get the intensity of that event. So that is your X value, and this is your D value. Now we can go ahead and solve here. We know how to solve this. This is a kind of rational, but it's the easiest kind of rational because it's just fractions. So I don't have to worry about my denominator being negative. I don't have to worry about extraneous solutions if it's just regular fractions. The LCD I'm going to use is going to be 18 because that incorporates both factors of 2 and 9. And I'm going to multiply everything by 18. Now, as I cancel, 18 over 2 is 9. So I'm looking at 9 times 7, which is 63. 18 over 9 is just 2. 2 times 1x is just 2x. Don't forget the x there. And 18 divided by 9 again is 2. And 2 times 26 is going to be 52. I'm going to keep solving. I'm going to bring that 52 to the other side. And let's see, I have 11 equals 2x. And then finally, I'm going to divide both sides by 2. I'm running out of room here. So I see that x is equal to 11/2. Or if I want to convert this over, it would be what, 5.5. If you find that easier as a decimal. So what the formula is showing us is that the high humor group averages a level of depression of 3.5 in response to a negative life event, such that the intensity of that event is 5.5. So the intensity is 5.5 in this case, when the level of depression is 3.5. And we can see that on the graph. So notice that the red line here is the high humor group, or the bottom line. So when x is 5.5, we're right around here, right? And if I go up, I see that point would be right there. So there's your value of 5.5 on the x-axis, and there's your value of 3.5 on the d-axis, I guess here. So this is x and this is d in this case. So we can see that our equation and our graph, so the visual and the algebra, all line up and match together. So just one application here of how we can use these linear and these rational equations, because I guess fractions can be both, to help us with some real world applications.